Tucker Goodrich, thanks for coming on the podcast, my friend. It's great to finally connect with you.
It's a pleasure, Paul. Really a pleasure.
There have been so many cool podcasts that I've been fortunate to do with Peter from Hyperlipid, Ben Bickman, and Brad Marshall from Fire in a Bottle that have been talking about this topic of linoleic acid metabolites. And so if people really want the full perspective here, you may need to listen to 3 or 4 podcasts in concert with this one. But my hope is that we'll be able to tie a lot of those things together and really go further down the linoleic acid rabbit hole specifically in this podcast, because this is something that you've been thinking about a lot, my friend.
Too much.
I don't know if it's possible to think about it too much. So as you guys all know, we will put the show notes at heartandsoil.co, which will have references. I may even post the Google Doc that Tucker and I will be looking at throughout this podcast so that you can all reference it. There will be a YouTube video, and the video will also be at heartandsoil.co. We will be showing many of the studies on the screen. I know many of you are listening to this on a podcast, so if you want to go back and listen to those, it'll all be there for you all. But, hopefully at the end of this podcast, Tucker, you and I can talk about ultra running and backcountry skiing, but let's just get right into the basics here. So on the podcast with Peter from Hyperlipid and Brad Marshall, we talked a lot about the electron transport chain. And I think we'll get to some rehashing of the electron transport chain, but let's just start with linoleic acid, because I say this word a lot, you say this word a lot, and I want everybody to understand what this is we are talking about.
Well, let me just make one quick point there. Peter at Hyperlipid is Dobromilski, am I getting it right? Is one of 2 bloggers where I've gone back to the beginning of their blog and read every single post that they have posted. So I will just posit, Brad's done a great job of popularizing Peter's work, but it's, at the end of the day, Peter's been the trailblazer down that avenue. And I'm just going to posit here that I agree with everything that he says. And what I'm going to try and do is add some context and some potentially countervailing mechanisms about what he describes. So if you want to go back and reference those 2, that's great. And I think you should, but I'm going to try and move the ball down the field from where those 2 would have left off.
Exactly. And I will do another podcast with Peter. I'm fortunate that Peter is going to come back on the podcast soon. We're going to continue the deep dive discussion with Peter at the level of the mitochondrial electron transport chain. And as you say, in this podcast, we're going to be talking about some things that are related and neighbors of those concepts, and we're going to extend the discussion.
Amen. That's exactly right. So linoleic acid. Linoleic acid is primarily a plant fatty acid. Animals do not produce it themselves. They get it by consuming plants. The richest source of linoleic acid in plants is mostly in seeds. So linoleic acid is a part of a real food diet. Pretty much no matter what you're eating, you're going to get some linoleic acid. I say that because people kind of go, oh my goodness, it's got some bad consequences. I shouldn't eat any at all. Well, you're eating some is fine. You're going to get some if you eat real food. In the 19th century, people came up with the idea of eating linoleic acid, which in large quantities, which has primarily been something that you didn't really see. In the United States, this started with the cottonseed oil business. Cottonseed oil had been a waste product from cotton production. And because of a nasty fatty acid called gossypol, it's quite toxic to humans. So in the 19th century, they figured out, they figured out how to take gossypol out of cottonseed oil and how to feed it to humans, which ultimately resulted in Crisco, which we've all heard of, which was a hydrogenated cottonseed oil. That was introduced in 1911. Prior to that, a lot of lard was adulterated with cottonseed oil, and this created a variety of big stinks in the United States and Canada, among other countries, when people realized that when they bought lard, they weren't actually getting lard, they were getting a blend of lard and cottonseed oil. Now, what's interesting about that is Scientists now use lard fed with a lot of seed oils, which has a similar fatty acid profile to lard and cottonseed oil, to induce obesity and metabolic dysfunction and all the other fun things we love to talk about when it comes to Western chronic diseases in animals. So this is kind of something that goes right to the root of all the questions that we're interested in, is this introduction of linoleic acid in large quantity into the human diet.
I love it. And as I've talked about before, and as you and others have talked about, there does appear to be an evolutionary inconsistency over the last 100 to 150 years in the amount of linoleic acid that we are consuming. It's not that we get none in a traditional whole foods, animal-based diet like our ancestors ate, but we got very, very small amounts because monogastric animals, even ruminants, don't make linoleic acid. Some animals store it more than others, but there has been this massive increase. And so if people saw also the podcast I did with Chris Kenobi, I would ask them to reference that as well regarding the history of the introduction of linoleic acid into the human diet. I'll just screen share for people who are watching on YouTube so everyone knows the molecule we're talking about. It's an 18 carbon omega-6 fatty acid with 2 polyunsaturations, these double bonds at the 9 and the 12 positions. And we'll talk about why those are relevant to the current discussion, but this is actually the molecule we're talking about. Again, humans.
And the key there is that little red 6 over the 12, which is the omega-6 position, 6 from the end of the molecule. That's why you call it an omega-6 fat.
Exactly.
Just as kind of a geek point.
Well, I think it's important so that people know what we're talking about. And that's linoleic acid. And again, it's not that there's none of it in our diet or there should be zero, but massive amounts. Could it possibly be driving the huge uptick that we've seen in chronic disease over the last 100 to 150 years? That's the hypothesis that we are going to be trying to corroborate in this podcast. So we can go from there.
There we go.
All right, so that's the basics of linoleic acid. Now, you, Tucker, have talked a lot about what can happen to linoleic acid. So let's just begin at the beginning and talk about how can linoleic acid become a bad thing for humans from your perspective?
Yeah, well, go right for the crux of the whole argument.
We got to.
So the problem with linoleic acid is polyunsaturated fats, like omega-6 fats, such as linoleic acid and arachidonic acid, and omega-3 fats, like fish oil, DHA, and alpha-linolenic acid, which is the plant omega-3 acid, all have these double bonds, which makes them, compared to a saturated fat, very susceptible to oxidative damage, right? They basically have as Paul just showed in that Wikipedia article, those 2 little double bonds provide a point at which other molecules, including oxygen and catalysts like iron, can attack the molecules and break them down. The linoleic acid per se is harmless, right? Linoleic acid can break down, however, into highly toxic substances. So what we're really interested when we're looking at human disease and linoleic acid is the substances that it's breaking down into. So for instance, for the topical reference, advanced respiratory distress syndrome, ARDS, right, which is what COVID-19 kills you with. It induces ARDS. Your susceptibility to ARDS is based on how much linoleic acid you have in your system. And the progression of ARDS is measured by how linoleic acid is broken down in your bloodstream into the linoleic acid metabolites, such as HNE and leukotoxin. And we can get into those later. So what we're really, and this confounds a lot of the epidemiological studies, because they say, oh, look, you have all this linoleic acid in your system and you're okay. Well, that's great. But that's in ARDS, when you're dying, your linoleic acid level is actually going down, right? That doesn't mean your health is getting better. That means it's converting into the toxins that are killing you. So this is a crucial point to make that far too many papers that I read don't seem to get.
And there is this breakdown of linoleic acid. And so the only thing I would add to that is the piece that I discussed with Peter and Brad. So at a protons level, in terms of the FADH2 to NADH ratio, lots of molecules with unsaturations may change the way the mitochondria can signal to the adipocyte, whether it's full or not. So that's a situation in which, quote, native linoleic acid, excess native linoleic acid might be harmful. But the majority of what we're going to talk about in this podcast are the breakdown products of linoleic acid, which is a whole separate chapter of why these molecules or how these molecules can be harmful. So really there are at least two potential ways or manners in which linoleic acid and its metabolites can be harmful to humans. This is essentially what Tucker is talking about. This is just a crude graphic from ResearchGate showing that linoleic acid can break down via either an enzymatic breakdown with 12-15 lipoxygenase or free radical oxygenation into 9 and 13 HPODE or 9 and 13 HODE, which we'll talk about. And there are many of these linoleic acid metabolites, but we have a molecule which is present in small amounts in ancestral human diets, present now in large amounts in our contemporary diet, that is very unstable and can break down into molecules which appear to cause lots of harm for humans. Is that kind of a good summary, Tucker?
It's a subset of the topic. So let me back up here a little bit, right? There's a molecule back to the mitochondria and where Peter works and where I work, right? Peter looks at the electron transport chain, which is basically how the mitochondria takes in substrates, food, right, like glucose or fats, and turns it into energy, ATP. I mean, I've never found him to be wrong on anything, so I'm just going to say, okay, everything that he says is right. But there's another factor in there, and it's a molecule called cardiolipin, okay? Cardiolipin is we're all familiar with triglycerides. Cardiolipin is a 4 fatty acid molecule that's uniquely found in mitochondria, bacteria, and chloroplasts in plants. Cardiolipin is what allows the electron transport chain to function. It's what moves protons along, moves electrons back, and it holds the mitochondria together. It gives its shape. It gives the mitochondria its shape. And the complexes that you talked to with Peter all are bound into cardiolipin, right? Into what they call supercomplexes. Cardiolipin is so critical that if cardiolipin is damaged or removed from the mitochondria, the entire mitochondria stops to function, okay? Now, this is essential to understand because cardiolipin fatty acid composition is determined in part by the diet. It's also determined by DNA, but it's determined in part by the diet. And importantly for our discussion here, if you increase your linoleic acid composition, you will change the composition of your cardiolipin in a lot of different tissues towards a more omega-6 fatty acid composition. Now, why is that important? Okay, cardiolipin is very subject to oxidation, okay? When cardiolipin gets oxidized, it first stops functioning as part of the electron transport chain. It won't allow the protons that Peter talks about to move down the transport chain and the electrons to move back. So it shuts down the electron transport chain. It also breaks down into these metabolites that we were talking about. So if you have And what's really interesting is cardiolipin is only subject to this oxidation when it's comprised of a lot of linoleic acid. So we're looking at what I think is the fundamental mechanism behind our mitochondrial dysfunction, our metabolic dysfunction, and our chronic diseases. Since mitochondrial dysfunction, as far as I've been able to find, is present in every single aspect of metabolic disease and is, as far as I've been able to tell, pretty much uniquely caused by this mechanism.
This breakdown of cardiolipin in the mitochondrial membrane. So again, we're in the mitochondria, which is an endosymbiotic organism traditionally or evolutionarily. This is a double layered organelle within our cells.
A bacteria that we have partnered with to live.
It's pretty incredible to think about. And I will screen share just to review the electron transport chain for people. This is again a diagram that I had with Peter. It's a very simplified diagram. You can see this is the outer membrane of the mitochondria, and the mitochondria is within the cell. So the cellular membrane would be outside of this. This is the outer membrane of the mitochondria, the inner membrane of the mitochondria, into which are inserted multiple proteins and supercomplexes, like Tucker's talking about, through which electrons move on the electron transport chain. This is things I talked about with Peter. So I would go back to that podcast if you need a review here. There's complex 1, complex 2. There's a Q here, a coenzyme Q couple, which can be reduced. There's a complex 3, a cytochrome C, which becomes important with cardiolipin as well, and a complex 4. So as electrons move down this chain, either being delivered at complex 1 from NADH or complex 2 from FADH2, in a very overly simplified view, they create a gradient and protons eventually move across the membrane and then back down through ATP synthetase. This is how we create ATP in the cell. And so what Tucker's describing here is all of these little guys with the blue heads and the tails. Many of these are actually cardiolipin. Cardiolipin is a molecule that exists within this membrane of the mitochondria. And I actually have some pictures of this, good old Wikipedia here as well.
Yeah, let me go to if I could, go to the diagram that I had in this outline that I put together.
Perfect.
So this is again, a somewhat less simplified picture of a mitochondria, right? These little loops that you see are what are known as the cristae. The cristae are composed of cardiolipin attached, and then the complexes are attached by a molecule called cytochrome C to the cristae, right? If you damage cardiolipin, you wind up getting a loss of the cristae structure, which, as this helpfully says, leads to sickness and a decreased cardiolipin level. What this means in vivo, to come down here to another paper that I love to discuss, the orange outline over in the lower right-hand corner is what a normal cardiolipin molecule looks like, right? And you can see these little squiggles throughout it. These are the cristae. The one that's circled in red is what happens to a mitochondria when you damage the cardiolipin through, in this case, excessive seed oil feeding, and then combined with hyperglycemia, it causes the mitochondria to collapse and basically to stop being able to function, which, as one can imagine, given how we've discussed how mitochondria and therefore cardiolipin are fundamental to life, is a bit of a problem, right? What this causes in the little chart B here, that little circle is what happens to a mitochondria's ability to burn glucose after you've fed it seed oils and then induced hyperglycemia. Basically, complex 1 collapses and fails, and it's unable to burn substrates, which in this model, this mouse study, which is my favorite study because it exhibits exactly what I'm trying to describe, is what happens in humans as they get older. They develop an inability to burn glucose and an ironic preference for fatty acids because their mitochondria are so damaged, which leads you to heart failure, which is what they are inducing in these mice in a few days through seed oil feeding and hyperglycemia.
It is very interesting to think about the number of conditions for which a ketogenic or low carbohydrate diet is beneficial in humans. Alzheimer's disease, many of the dementias, the neurocognitive disorders, and how they have been connected with things like mitochondrial dysfunction. And if this is actually what's going on, I think there's a really strong case for it. That is really fascinating, that it's not so much the mitochondria themselves breaking, it's that through a lifetime, apparently, or possibly, of overfeeding of linoleic acid, we as humans are breaking our mitochondria and eventually potentially breaking complex number 1. If you go back to the diagram of the electron transport chain, you will see that complex 1 is where you get the NADH inputs. And if the listener is familiar with the podcast from Peter, most of these NADH inputs are coming, or many of the NADH inputs are coming from glucose or carbohydrates. So I want to highlight the fact that it's not necessarily the carbohydrates per se that are problematic, but potentially if we are overfeeding ourselves, like these poor mice, with excess omega-6s for our whole life, we could end up in a position where our mitochondria get broken, or the complex 1 in the mitochondria become diseased, leading to a real impairment of that complex 1 driven electron transport chain, sort of movement of electrons and oxidative phosphorylation. I have a number of these papers up. I'll just pull them up so that listeners can actually look at the papers if they want, because these are so interesting. And the first one you were showing there is the paper from Ghosh. And actually you showed the one from Kojima and then the one from Ghosh, and I will pull both of those up. So this is the paper from Kojima. If people want to find this paper, we'll put it in the show notes. You guys, again, the title is Maintenance of Cardiolipin and Crista Structure Requires Cooperative Functions of Mitochondrial Dynamics, Phospholipid Transport. This is the diagram that Tucker was showing with the cristae kind of collapsing when cardiolipin becomes damaged. And I love what you're saying there, Tucker, that it apparently is quite possible through excess overfeeding of linoleic acid to enrich the cardiolipin with linoleic acid, which makes it susceptible to breakdown. This may be helpful to show people this as well. The actual structure of cardiolipin, which is kind of hard to wrap your head around, but it has 4 diacylglycerols. So these 4 chains linked up here. So as Tucker mentioned in the beginning, there's a triglyceride, which has 3 diacylglycerols. Cardiolipin has 4, and it is these tails, these fatty acid tails, that we are talking about becoming more or less enriched with linoleic acid based on dietary composition. Would you agree with all that, Tucker?
That's exactly right. Now, I've included in my document a couple of posts of mine, one of which is titled uncontroversially, here, let me just scroll down. One of which is titled uncontroversially, the cause of metabolic syndrome, excess omega-6 fats, linoleic acid in your mitochondria. So no room for argument there. What's really interesting about this, when you look in the literature, not only is the cardiolipin composition of mitochondria controlled in part by diet, oxidation, the damage to the cardiolipin is an oxidative process, right? So you have in the mitochondria reactive oxygen species that are being generated. These can go and oxidize linoleic acid in the cardiolipin, thereby breaking the cardiolipin. What's not as well recognized is that cardiolipin is attached to cytochrome C, which is a heme molecule, okay? Hemoglobin is made in the body by mitochondria, oddly enough. And there's a lot of iron in the mitochondria in these cytochrome C molecules. When a cardiolipin molecule is comprised of linoleic acid, it gets the ability to deform the cardiolipin or the cytochrome C molecule, exposing the cardiolipin to the iron molecule and thus oxidizing the linoleic acid. So in the mitochondria, linoleic acid is actually able to auto-oxidize, right? When it auto-oxidizes, it releases these metabolites, which we will get to. The metabolites can then go into adjacent cardiolipin molecules and cause them to break down. So you have, you showed that pathway, the LOX pathway at the beginning. This is an entirely independent, non-enzymatic pathway of linoleic acid degeneration in the body, where literally the proximity of a cardiolipin molecule containing excess linoleic acid is able to break itself down in the mitochondria. And what's interesting is scientists have gone in and replaced linoleic acid with oleic acid and done various other similar experiments. Cardiolipin are only subject to this sort of oxidative damage when they're comprised of linoleic acid. So it's a real bottleneck in this process of metabolic dysfunction, right? This seems to have to happen for everything else to happen afterwards.
And it all kind of comes back to an evolutionarily inconsistent consumption, overconsumption of this fatty acid that's pretty rare in nature, generally found in seeds, but not found a lot of other places, that in the last 150 years we've been consuming in massive quantities. There is a diagram here. Sorry, go ahead.
No, and I wanted to say there are a couple of things that drive me bananas in the literature when you go through and read it. The first is that cardiolipin is primarily comprised of linoleic acid. This is just false. And you can find lots of papers looking at all the different cardiolipin species and the effects of different fatty acid composition on the susceptibility of cardiolipin to oxidation, right? So that statement's clearly false. The other statement that's at this point clearly false is you will often hear people saying, oh, you should eat seed oils because polyunsaturated fats, because it's an essential fat in the diet, right? So this was initially shown in rodent studies back in the 1930s. It has since been debunked in humans and in rodents. Linoleic acid is not an essential fatty acid for humans. The longer chain N3 and N6 fatty acids, DHA and arachidonic acid, are in fact essential. And they just, this was demonstrated in rodents and then assumed for humans. They've shown in a recent study that they can maintain rodents for 10 generations, right? Essential means required for life and must be consumed from outside the body. So in rodents, for 10 generations, you cannot get any linoleic acid, just get DHA and you're fine. And they've done similar clinical work in humans showing that essential fatty acid deficiency in humans can be cured with DHA and just potentially a tiny little bit of LA. And they actually had a woman who refused a fatty acid supplement and was nevertheless able to give birth to 2 healthy children in an essential fatty acid deficient state, which pretty much tells us that that idea was bogus. So if you hear that you should be consuming seed oils because they're essential, you can snort derisively and say, well, that's not what the science says, because that's the fact.
I love that, because as I have started talking more about linoleic acid, some have commented in response, how can this be bad for us? It's an essential fatty acid. To which my response has been, potentially, but the amount is what's important, and we don't need very much. And so I love that you're highlighting the fact that it's essentially not even essential. This is essentially not essential. And
it's literally not essential.
Not essential.
I mean, the rodent studies that originally showed that have been overturned.
And in previous podcasts, I have shown the parallel synthetic pathways between omega-3 and omega-6 fatty acids. I can show that now if it's helpful for people.
And one more quick point, though, right? That's kind of a key point for a doctor who espouses a carnivore diet is DHA and arachidonic acid are both found abundantly, sufficiently in animal fats. So based on the science at this point, you could legitimately get by on just the fatty acid from animal without any requirement for any plant fatty acids.
I completely agree. And I am a huge fan of animal fats over plant fats. Just full stop, end of story. Whenever I talk about linoleic acid and seed oils, people always ask me, what do you use for cooking? And I always say tallow. Why would you not just use animal fat? Don't use lard. Butter. Yeah. If you're not sensitive to the whey and the casein in dairy, you can use butter or ghee. I prefer tallow or suet. These are the fats that our human ancestors have been using for millions of years. You don't need olive oil. You don't even need coconut oil. They are missing the benefits of animal fats. They don't have as much stearic acid. They don't have pentadecanoic acid. They don't have fat-soluble vitamins like vitamin K2. So animal fats, in my opinion, are clearly more beneficial and have always been favored by humans. How interesting that they've been vilified for so long. If you're still concerned about the vilification of saturated animal fat, you should go back and listen to the podcast I did with Nina Teicholz, in which we talked about that debacle as well.
But yes, completely agree.
Yeah. So I'll show this diagram from Wikipedia, which perhaps is illustrating what you were mentioning earlier, Tucker, that cardiolipin is in the membrane. It is associated with cytochrome C. It can become oxidized. And there is also this mechanism by which then cytochrome C can be released from the membrane, leading to apoptosis or cellular death as a sort of bad mechanism downstream from cardiolipin peroxidation. But the ultimate determiner here is probably the linoleic acid composition of these four tails of the cardiolipin molecule in the membrane. These are all phospholipids that are next to the cardiolipin. And as we've been talking about, there are electrons, which are negatively charged particles being passed through the membrane. There's a lot of possibility of oxidation. And if we over fortify, that's the wrong word, but if we over consume linoleic acid and the cardiolipin becomes overly enriched in linoleic acid, it could lead to massive problems. I also want to show the other study that I mentioned from Ghosh, because I think people will find this one quite interesting. This was the one that you were showing the photos of. And so if people actually want to read this study, this is a brief episode of streptozotocin-induced hyperglycemia produces cardiac abnormalities in rats fed a diet rich in N6 PUFA. As we said in the beginning of the podcast, N6 PUFA is essentially linoleic acid and omega-6. And you can see that there are there's a lot of evidence of actual cellular death, cardiac cell necrosis, and problems with cardiac function in these mice when they become hyperglycemic on an excess polyunsaturated N6 diet. Thus, although promoted as being beneficial, excess omega-6 polyunsaturated fat with its predisposition to induce obesity, that's the kind of stuff I talk about with Peter, insulin resistance, that's interesting as well, and ultimately diabetes could accelerate myocardial abnormalities in diabetic patients. Those are pretty strong words. It's pretty awesome to see those in that paper. They've got some interesting graphics here. You guys can actually see how.
Okay, so perfect, because I was just looking on my blog. I did a long blog post going through this paper. It is one of the funniest scientific papers I've ever read, because I'm quite convinced that these guys knew exactly what they were doing when they wrote this paper. So what they start out doing is by saying that polyunsaturated fats can decrease apoptosis, and this is a good thing, okay? So, okay, fine. Apoptosis is a controlled cell death pattern, right? Where it started in the mitochondria says we have a problem here, and the cell says, okay, we have enough mitochondria who have a problem,
and they just wave to the bouncer and say, you know, we're too drunk to continue anymore. Please take us out of the bar. We're done, right? Okay, that's great. So what they show is that indeed polyunsaturated fats decrease apoptosis, but they do it by shifting the cell into what's called necrosis. Now, if apoptosis is the guy at the bar saying, I'm too drunk, please get me out of here, necrosis is the guy at the bar starting a fight and throwing up all over the place, right? It is uncontrolled cell death. And it is what seems to be fundamental to the later stages of a lot of these metabolic dysfunctions like Alzheimer's and, you know, liver failure and heart failure. So what they show is that by upgrading the seed oil composition, they break down the mitochondria, they cut down the level of cardiolipin in the mitochondria, and then they add hyperglycemia to it, and they induce a shift from apoptosis to necrosis in the heart tissue and cause heart failure, right? So they are indeed demonstrating that it does reduce apoptosis, but it does it by causing something far worse in your body. It's an absolutely brilliant paper because it's such a clear demonstration of what these things are doing to your body if you're a mouse. And I start off my post with a bit of a, you know, a chart on how much more common heart disease has become in humans over the last few decades. And then the paper's a demonstration of how do you induce heart failure through seed oil consumption.
Exactly. And I love that you mentioned this, Tucker, that this is a mouse model, but whenever we're using a mouse model, we sort of have to ask ourselves, how relevant is this to humans? And as I discussed in the podcast with Brad Marshall, many of the things we are looking at here are conserved all the way down to C. elegans through fruit flies and mice. And so we are talking about mitochondria. We are talking about endosymbiosis. We are talking about cardiolipin in a cellular membrane of an electron transport chain. These are all pretty highly conserved. So this is a mouse model because we haven't been able to do this in humans, but it is pretty darn relevant to humans from my perspective. But I'd be curious for your thoughts on how relevant some of these mouse studies are to humans from that perspective.
You're taking a lot of the fun out of my talk here, Paul, because
I'm sorry, why?
You're anticipating some of my best talking points.
Oh, I didn't mean to. I'm sorry.
Well, that's a testimony to your familiarity with these topics, because that's absolutely correct. Mitochondria, I mean, we're talking about mechanisms that are so fundamental that they're not only common between mice and humans, but they're common between humans and plants. Right. So when I was going through some of the mechanisms of linoleic acid breakdown, you start getting into papers on plant diseases because linoleic acid oxidation is also a problem over there. So this is an incredibly common mechanism. And while the, you know, for instance, in that paper, when they induce hyperglycemia in mice are a little different in humans in a couple of ways that are well demonstrated in this paper. For instance, increasing their seed oil intake gives them the mouse equivalent of diabetes, where they get hyperinsulinemia and hyperleptinemia, right, which is both high levels of insulin and high levels of leptin, but they don't get hyperglycemia. Mice don't get hyperglycemia in their equivalent of type 2 diabetes. So what they have to do is kill their beta cells, and that induces hyperglycemia. When you induce failure of half of their beta cells, they get severe heart failure in 4 days. Okay, this is very different from what happens in humans. Humans get hyperglycemia as part of type 2 diabetes, but heart failure can take decades to come on. So there are a lot of, you know, it's a good model, but as always with mouse studies, one has to be really careful about extrapolating it back to humans without some context.
So I guess the next question would be, what evidence have you seen that we could reasonably extrapolate this back to humans in terms of heart failure? You mentioned that heart failure is something that's been increasing. Certainly cardiovascular disease in general has been skyrocketing, and that gets into mechanisms of atherosclerosis, which we'll save potentially for a separate podcast. But what do you think? I mean, how translatable are these mechanisms in mice with the mitochondria to humans?
Well, they seem to be directly translatable. A lot of the, I came across a paper, which I didn't include here, that looked at what happens to elderly people, and they suffer from a decline in their ability to oxidize glucose, just like in this paper. Mitochondrial dysfunction is a fundamental aspect of heart failure in humans. Fibrosis, which we'll get into as another aspect of linoleic acid peroxidation, is a common factor in heart failure. For instance, atrial fibrillation also often occurs years, decades prior to heart failure appearing, and is heavily associated with fibrosis in the heart, which is basically a breakdown in the muscle fibers in the heart, which obviously, since the heart's a very busy muscle, the muscle fibers breaking down are a bit of a problem. We also need to look at, back to, just a quick aside on epidemiology. I got this example from Gary Taub, so let's give him credit. But in one of his books, he describes epidemiologists as being like a drunk guy looking for his car keys. So the policeman walks up the road, and there's a guy crawling around on the street in front of a bar under a streetlight. And the cop says, "What are you doing?" And he says, "Well, I'm looking for my car keys." And he says, "Well, where did you drop my car keys?" And he points down the road and he says, "Over there." And he says, "Well, why are you looking here?" And he said, "Well, this is where the light is," right? This is human epidemiology in a nutshell. Epidemiology is a science started, 50s pretty much with Ansel Keys. Seed oils were introduced in the late 1900s, right? There's a lot of epidemiology looking at the effect of seed oils on human health, and they all look at populations that have been eating seed oils for decades, right? They never look at populations that don't look at seed oils. When you start looking at populations that don't look at seed oils, like the Catawbans, the Tsimane down in Latin America, or the Eskimos prior to the introduction of Western foods, or you go through Weston Price's work, what you realize is that the people who don't eat seed oils don't ever have any of these problems that we're going to talk about today. That's a fundamental problem with epidemiological research, starting with Ansel Keys, is that he did the research in the countries that had an advanced academic system where they could support his research project. But that meant he's looking at, countries in Europe and Japan and Asia. He's not looking at, the Amazon jungle in Latin America, in South America. He's only looking at the people who've already been on an American-style diet for decades. It's a real fundamental problem with the field.
And I've talked about this in the past as well. If you're looking at dirty water, all of your associations are going to look differently. There's a paper that I've talked about multiple times suggesting that only 12% of the US population, I think based on a 2016 survey, is free from any of the markers of metabolic syndrome. Therefore, 88% of the population has at least one indicator of metabolic unhealth. And this will come up in future podcasts that I will do with people discussing lipids. But if your entire population, or the majority of the population you're surveying, is sick, is metabolically unwell, you may see correlations that are not reflective of otherwise metabolically healthy individuals. That is why I think that epidemiology, for all of its limitations, looking at cultures like the Catawbans, the Tavaruans, the Tucasinta, the Kaiwi-Meno, the Tsimane, the Nigerian Yoruba, there's so many of these populations, the Hadza, these people don't have the same incidence of cardiovascular disease that we do, and they eat tons of saturated fat. Many of them eat carbohydrates, but what do they do differently than humans? in the westernized countries, they don't eat seed oils. Well, that's a really interesting correlation. We can't draw a causative inference, but we can draw some really compelling hypotheses, which we are exploring here today. But we must not be confused by large volumes of epidemiology done in dirty water, quote unquote, done in populations that are metabolically unhealthy. Garbage in, garbage out. You can give me a mountain of garbage and it's still garbage. You can do a meta-analysis of garbage and everybody in there is garbage. So
yes, that's exactly right. This is something that I've talked to Sean Baker about over the years as regards lab values, right? So the lab values that you get back in standard tests their normal is a statistical normal based on the population that they're looking at, who, as you just described, are 90% sick. So they never go out and look at healthy populations. They never go out and look at a population that has a 0 rate of heart disease or a 0 rate of cancer effectively. I mean, some of these populations are literally that close. All they're looking at is sick people, and they're saying, you know, this marker is healthy because it's in this normal statistical range, but it doesn't mean normal in the sense of having a healthy outcome. It means statistically normal because it's in a band based on the numbers of the rest of the sick people that we're looking at. That's not really a valid way to do this sort of science, in my opinion.
I completely agree with you, and I appreciate you bringing that up. I'll just share the rest of the screenshots from this Gauche paper because they're really cool. These are the ones we were looking at earlier: the healthy mitochondria, the broken mitochondria. And here's a graph in the paper. You can look at cardiolipin on the y-axis on the normal diet. Here they made them diabetic with streptozocin, which is part of the mouse model. But look at the N6 PUFA diet. Look at the cardiolipin levels. They're a fraction of what they are on a normal diet in mice. So that's
so even the mice that are poisoned to make them type 1 diabetic are healthier than the mice that are fed seed oils and not poisoned, which tells you from a toxicology perspective that seed oils are a worse toxin metabolically than the poison that they're using to make these mice into type 1 diabetics. That's just an amazing finding.
It's pretty striking. And there are all sorts of graphics in this paper if you guys want to look at it. Reduced to oxidized glutathione ratio, oxidized glutathione, reduced glutathione, and not surprisingly, the N6 PUFA diet decreases reduced glutathione, increases oxidized glutathione, at least in the group that was made hyperglycemic, and the ratio is very different.
And that's a great point to what I was saying before about linoleic acid and not understanding the processes that are going on. If you look at these two charts and you understand what's happening to linoleic acid in this cell, this makes perfect sense, because linoleic acid in cardiolipin, as we can discuss later on, is breaking down into a substance called HNE. The point of glutathione is to remove HNE from the cell. And in the course of doing that, it is converting from reduced glutathione to oxidized glutathione. So what you are seeing in these charts is the marker of linoleic acid breaking down into a toxin in the cell, and the cell struggling to reduce it from the cell.
It's really a great paper. It illustrates a lot. I hope people will check that out if they have questions. And then let's move on to talk about HNE. I just want to mention this one paper, which you may have sent this to me, or I found it. I'll say I've got a feeling you sent this one to me. So circulating levels of linoleic acid and HDL-cholesterol are major determinants of 4-HNE protein adducts in patients with heart failure. The reason I thought this is relevant to our current conversation is because this is looking at humans with heart failure. The previous discussion was mice with heart failure, but these are humans with heart failure. And the group is looking at 4-HNE, which we're going to get to right now. It's an oxidative product of linoleic acid metabolism. And they were looking at ambulatory symptomatic heart failure patients. And they found that the 4-HNE levels in heart failure patients they had a regression analysis that revealed that linoleic acid was the only factor that was significantly associated with circulating 4-HNEP in the entire population. 4-HNEP was even more strongly associated with linoleic acid in heart failure patients. And there is some connection here, even in humans, that this could be going on. They say results from the study emphasize the importance of considering changes in lipids and lipoproteins in the interpretation of measurement of lipid peroxidation products. Further studies are warranted. Well,
and so a little context on that. HNE is highly reactive, so it can't be detected directly because it reacts with proteins, lipids in the body. So often what they will look at for these studies is protein adducts, right? Where you have a protein that has a 4-HNE molecule attached to it. That's a better marker of actual damage in the body than just looking at HNE alone, which is gone by the time you're looking for it. So what they're looking at is damaged proteins, and they're saying that HNE damaged proteins are increased in the heart failure population, which is what you would expect to see, because in order to do damage, HNE has to alter the function of proteins, and we can get to that. I'd like to, since the premise of this was the metabolites, can we just zip through the metabolites a little bit and then get to HNE so we
absolutely, yeah, let's talk about the metabolites.
Some scope about what we're talking about. Now, one of the interesting things, linoleic acid metabolites have been called oxylipins, which means oxidized lipids, or OxLAMs, oxidized linoleic acid metabolites. Oxylipins seems to be more commonly used, so I'll just use that. When linoleic acid breaks down in the cell, it can break down into a variety of different substances. Some of them are super toxic and highly reactive and are virtually untrackable in the body. Others, like HNE, are moderately toxic and moderately trackable in the body. So those are the ones. HNE is the most commonly studied. There are a few other ones that I'd like to, just mention in passing, but it's a big field. Just to zip back to my little document here, just to give people a little bit of context. Hold on. Here we go. So this is a Word doc that I put together based on some PubMed studies. Linoleic, not conjugated to avoid conjugated linoleic acid, which we're not going to get into, but it's something that you find in dairy and animal products, and it's very healthful, apparently, because it blocks linoleic acid. Isn't that a funny thing? But anyway, if you're looking for the effects of linoleic acid, you have to avoid looking at that. So that's about 23,000 results. If you look at HNE, which we just discussed, but not human neutrophil elastase, which is another HNE that we don't want to talk about, you're looking at about 3,000 results. But if you're looking at the larger topic, which is oxidative stress, and effectively oxidative stress in the body means the oxidation of N6 fats, you're looking about 240,000 results. So this is a big topic. So when I hear people say, oh, your claims that oxidative stress is a problem are baseless, there's no evidence for this, there's a huge evidence base for this topic. It's not just me, right? There's 240,000 odd papers out there looking at the topic with various degrees of success. We'll just skip through some of this stuff. Notable metabolites of linoleic acid. Oxidized cardiolipin is probably the first one to discuss because we've already talked about that. There's a human autoimmune disease called antiphospholipid syndrome, where basically the body becomes allergic to its own phospholipids. If you drill down on that, you'll discover that what's happening is the body is becoming allergic to oxidized cardiolipin. as we've discussed, oxidized cardiolipin means oxidized linoleic acid in cardiolipin. So this is basically a direct induction of a human disease by the pathway that I've described. Oxidized anti-cardiolipin antibodies are found in things like lupus, heart failure, where else? Lupus, heart failure, fibromyalgia,
chronic fatigue syndrome, atherosclerosis.
Atherosclerosis, yes, thank you. So this is, appears to be pretty fundamental, although I've not been able to find anything that explains how it's pathological, just that it's associated. For some of the mitochondrially connected diseases like lupus, chronic fatigue syndrome, and fibromyalgia, it appears to be a pretty direct connection. There's a fellow on Twitter who was a physicist who had chronic fatigue syndrome and was able to put it into remission after coming across some of my rantings on linoleic acid. And I've helped a number of people with fibromyalgia put it into remission just by cutting back on their seed oils. So
That's
I think
so cool.
In that case, it's a pretty direct connection between seed oil intake and mitochondrial dysfunction, evidenced probably through necrosis releasing oxidized linoleic acid in cardiolipin into the bloodstream, which is why they're seeing those antibodies. So that's oxidized cardiolipin. That's pretty interesting. The other one that's a huge topic is oxidized LDL. Now this, Paul, with your, I've heard, astronomical LDL levels, is probably a pretty interesting topic. Back in the 80s, Brown and Goldstein discovered the LDL receptor and got a Nobel Prize for it. The next thing that they tried to do was to incubate LDL with macrophages to turn them into foam cells, which was at the time recognized as the first, and it was thought, initiating step in atherosclerosis, right? Makes sense. You think LDL is the cause, put it in there with the foam cells, you should see, or with the macrophages. Problem was it didn't work. Oops, bummer. So much, by the way, for the LDL causes atherosclerosis argument, although there's a lot more evidence for that. So then these two other fellows, Steinberg and Whitstam, came along and discovered that in order for LDL to induce macrophages, which are a type of white blood cell that's kind of critical in a lot of these diseases that we'll talk about, to turn into foam cells, you had to first oxidize the LDL, okay? So what does an oxidized LDL look like? Oops, my computer's not cooperating here. An oxidized LDL is an LDL in which the omega-6 fatty acids have oxidized. That means the linoleic acid and the arachidonic acid has been converted into two linoleic acid and arachidonic acid metabolites, MDA and HNE, and we will get into those a little later. When that happens, macrophages will hoover up oxidized LDL until they become foam cells. So back to that lovely term essential, it turns out that oxidized LDL and therefore the oxidation of N6 fats is essential to the initiation of atherosclerosis in humans, okay? So Steinberg and Whitstam then went along and said, okay, well, let's test this. And there are a number of studies that show the same thing. As far as I know, they were the first where they put rabbits on two different diets, one with seed oils and one with olive oil, which doesn't have much linoleic acid. And then they tried to oxidize their LDL, and they found out that olive oil protects and seed oils promote oxidation of LDL. They then did the same things with humans and found the same process. Steinberg then went on to become the biggest fan of statins and dropped the whole research topic, which I can't tell you how frustrating I find. Chris Masterjohn has done some rather brilliant analysis of Steinberg's somewhat incomprehensible abandonment of this whole field of research in favor of promoting statins, which makes a certain amount of sense, because if you really do think that nobody's going to change their diet, there's, I will certainly concede that statins do seem to be protective against heart disease, and they do seem to be protective against this oxidative pathway, but the effect of statins is around 20% in protecting you against cardiovascular disease. The one study I'm aware of that actually explicitly lowered N6 fats in humans, the Lyon Diet Heart study, reduced it by around 70%. So given those two alternatives, I'd skip, I'd fix the cause. I wouldn't try and put a Band-Aid on it. Anyway, so
I agree. Yeah, I love it.
So that's oxidized LDL is it. So one of the interesting things about type 2 diabetes, kids who get insulin resistant come down with increased rates of OxLDL about 10 years before they actually get insulin resistant. OxLDL kills the beta cells in the pancreas directly. It is apparently potentially causative in prostate disease, prostate cancer, through the CD36 receptor, which is what macrophages use to hoover up oxidized LDL. And there's just one of my favorite studies on this topic is, we'll kind of get into this a little later, but there is an antibody against oxidized LDL looking at MDA. If you take a rhesus monkey and you make him fat and obese through feeding him Kool-Aid, and I'm not kidding you, right? And we can get into at some point the inner, actually it's very similar to what happened with those mice. You give them seed oils and then you give them hyperglycemia and they get really sick. So if you give rhesus monkeys Kool-Aid, they get sick. No kidding. But if you give them an antibody against oxidized LDL, you cure their insulin resistance. That's bizarre, right?
That's interesting. It's very interesting.
And there are 3 human studies that show the same thing effectively, since we know that oxidized LDL is produced by seed oils in the diet. There are 3 human studies that reduce insulin resistance by cutting down on seed oils, even if they don't cut down on the carbohydrate portion of the diet. 2 of those studies had a 75 to 80% carbohydrate diet, and they were able to cause weight loss and a reduction in insulin resistance just by cutting back on seed oils. So, and I would wager, based on the rhesus study, that that's through the effect on oxidized LDL. So that's a huge topic.
Can I pause you there for a moment?
Yeah, no problem.
I'll just comment. There are lots of podcasts coming on LDL. If people heard the Joe Rogan episode or they've seen what I've been talking about recently, my recent LDL was 533 milligrams per deciliter, but I have a coronary artery calcium score of 0. I'm going to get a coronary angiogram, so a CT coronary angiogram in the future. But the really interesting test that I'm going to do probably next week is oxidized phospholipids on ApoB. And I talked about this in the podcast with Dave Feldman, you guys. So go back and listen to that one. And I think that
Dave and I have had great discussions on that. Definitely listen to that podcast. That's a really key topic.
And Dave has a, quote, elevated LDL as well. And yet his oxidized phospholipid on ApoB, when he checked it through Boston Heart, is very low. I would expect mine to also be low, but I will have to prove that with my own laboratory analyses. Now, I'll just be clear for people so they understand. The debate is not whether LDL or ApoB containing particles get pulled into atherosclerotic plaques. The debate is whether they initiate those plaques on their own de novo, in which case, if LDL itself does not possess a little sword that it goes around creating all this havoc with, then having a bunch of LDL might not be a bad thing if a very small amount of it is oxidized. And that's the hypothesis that I and many others are operating from with regard to the LDL. So that's a preview of things to come.
Let's be a little fair, though. I got into a discussion with a physician on Twitter over the last couple of days. As far as I'm aware, the overwhelming body of evidence in the scientific and medical literature is that oxidized LDL is at least required and certainly central to the whole progression of atherosclerosis. As far as I'm aware, there is no other alternative hypothesis offered, right? This goes all the way back to the 1980s and Brown and Goldstein and Steinberg and Whitstone looking for how LDL would initiate atherosclerosis and finding that it had to be oxidized in order to do it. Nobody's ever debunked those findings that I'm aware of.
I don't think so.
So this isn't, you're not going out on a limb here. This is, to anybody who spends any time reading the scientific literature, this is the evidence, right? This is it. This is the only viable hypothesis that I'm aware of.
And I think it's widely accepted that native LDL does not initiate atherosclerosis, that native LDL will not get taken up by the macrophage in the subendothelial space. And yet people lose their mind when I show my LDL of 533. I'm a pretty strong lean mass hyperresponder. I suspect some of that LDL may have been driven up by consumption of honey. And so I'm doing a lower fructose experiment or a zero fructose experiment now, and I'll recheck my lipids. But as people can see on all my blood work, which are at the JRE show notes at heartandsoil.co/Rogan, my HDL was 90 and my triglycerides were also low. My CRP is low. So it challenges the theories really straight on. Now, I apologize in advance, Tucker, if you were going to show these studies, but I want to show two really key studies at this point in the discussion. And again, I don't mean to steal your thunder.
You've been doing great so far, so I'm sure you are going to steal my thunder, but I'm happy to see it. There you go. That's a great one. Ramsden. Yep, that's brilliant.
So just so people understand what we're talking about here, we'll link to all these in the show notes. There are some pretty good studies showing that lowering dietary linoleic acid reduces bioactive oxidized linoleic acid metabolites in humans, okay? The results show that lowering dietary linoleic acid can reduce the synthesis and or accumulation of oxidized linoleic acid derivatives that have been implicated in a variety of pathological conditions. This is just pretty solid study from 2012. Chris Ramsden is a national hero. I want to get a t-shirt with him on it. Maybe I'll get him on the podcast at some point.
I'll buy one.
Yeah, right. Chris Ramsden should be running for political office, no matter who you're voting for. So that's an interesting one. And then this one is also relevant to the conversation of oxidized LDL. We can come back to either or both of these in the future if you would like, Tucker. This is a paper showing a strong increase in hydroxy fatty acids derived from linoleic acid in human low-density lipoproteins of atherosclerotic patients. I've shown these studies before, guys, but I'd like to bring them up because the themes are repetitive. And you can see that in this paper, and we'll get into more of this, they looked at the 9-hode content of LDL in healthy volunteers, 17 atherosclerotic patients of a younger age group, and then they looked at 20 healthy volunteers and elderly people. And the amount of 9-hode in the LDL of those with atherosclerosis was increased by huge factors, a factor of 20 in the younger age group and a factor of 30 to 100 in the older age group. The way that I read this, Tucker, and I'd be curious for your interpretation, is this is pretty good evidence that these are linoleic acid metabolites in the LDL becoming oxidized, which are much higher, 30 to 100-fold higher in the group that is developing LDL and is developing atherosclerosis, excuse me.
Yeah, that's Spitaler. He's got a lot of great work in this area. There are a couple of things that you got to understand when you're reading the medical literature, right, to understand this stuff. The definition of oxidized LDL is LDL with oxidized omega-6 fatty acids in it. Yeah. That is the definition, right? So this paper showing that that's what's happening is not surprising because that's the definition of it, right? The definition of oxidative stress, which, we're kind of talking around, but it's the term for the central process that we're looking at here. The markers that they look at to measure that are all omega-6 fatty acid metabolites. So saying that this is central to these processes isn't you and I being radical. It's the definition of what these processes are, right? OxLDL by definition is oxidized omega-6 fats, period, end of story. That's what's happening, right? Go ahead.
And there seems to be a good amount of evidence, correct me if I'm wrong, that the connecting piece of the hypothesis would then be, if we eat more linoleic acid, is our LDL enriched in linoleic acid?
And it's been shown repeatedly in human studies that that happens, and that when that happens, the LDL becomes more oxidized, right? Now, there are other factors in there. So for instance, if you eat a lot of fructose, that'll increase your OxLDL levels through what happens through fructose metabolism in the gut. One of my favorite studies, just to go back to your metabolite study, if you can just bear with me for a second here. Let me see if I can pull this up. Just humor me here for a second. There was a great Polish pilot study. Here we go. This is lovely. So here we go. Can you see this? Metabolites of arachidonic acid and linoleic acid in early stages of non-alcoholic fatty liver disease. Now, non-alcoholic fatty liver disease is a new disease that emerged, I think, in the 50s and the 60s. And I'm not going to go into any commentary on that, okay? But let's look at what they do here. They get, following the 6-month dietary intervention, hepatic steatosis, which is an incurable condition. Non-alcoholic fatty liver disease is in 20 to 30% of Americans. It's incurable, right? There is no known treatment other than weight loss, which isn't super helpful. So they put these folks on a low linoleic acid diet, high carbohydrate, but low linoleic acid diet, and they get a 100% cure rate of NAFLD, actually steatosis, but it's a later stage of the same disease. 100% cure rate. I mean, people go on about P equals 0.5 or 0.05 or whatever the number is. This is 100% cure rate. You never see this in the medical literature. Never, never. And when you go through, they're talking about a lot more stuff than we're going to talk about here with linoleic acid metabolites, but that's what they're measuring, and that's what's going down. And they're seeing BMI go down, insulin go down, HOMA-IR go down, which is a marker of insulin resistance, liver enzymes go down to 100% cure rate. That's just mind-boggling.
It's amazing. Will you go scroll up to the title again so people can see it? We'll link to it in the show notes also.
Yeah, metabolites of arachidonic acid and linoleic acid in early stages of non-alcoholic fatty liver disease. Huge study that, it's a mystery to me. When is this from? 2015. Why hasn't this been reproduced? I mean, there's literally nothing. Look at COVID-19. These people, the people who were cured in this study, are the people who are most susceptible to COVID-19. And this has been completely overlooked in the medical literature that I'm aware of. It's crazy. It's crazy. Anyway, without too much editorial comment, I sometimes get a little worked up about this. So anyway, let's go back to some other fun things. So this is just a real quick share here. This is what happens to LDL. Free HNE and total MDA and native low-density lipoproteins and LDL, oxidized low-density lipoproteins, and glycated low-density lipoproteins, right? So what you can see is that native LDL and LDL has a very low level of oxidized N6 fats. Oxidized LDL has a very high level of oxidized N6 fats, and glycated LDL has an intermediate level. So that's just, this is oxidized outside the body, so it's not a perfect model, but it shows you what happens to LDL with a lot of N6 fats. This second little here is another study looking at what happens when you block OX-LDL and how it reduces insulin resistance in these rhesus monkeys.
And that's
kind of a fascinating little paper.
And that's looking at the macrophage here with the receptors for oxidized LDL, elaborating inflammatory cytokines, and so they're sort of blocking the inflammatory response at the level of the macrophage. Am I looking at that properly?
That's right. Now it's interesting because it blocks, it lowered insulin resistance, but it didn't actually make a huge difference in atherosclerosis, which is why they were doing this study in the first place. And I have some thoughts on that are kind of off topic, but it did have a significant impact on insulin resistance, which is a pretty interesting finding. Other metabolites we should discuss here real quickly. Leukotoxin is leukotoxin is produced by leukocytes, hence the name. Leukotoxin, we mentioned ARDS before. Leukotoxin is what causes death in ARDS, right? It causes all the symptoms. This has been known for quite a while. I forget the date on this paper, but it goes back a long time, long before COVID-19 came around. If you have high levels of N6 fats, you are more susceptible to a bad outcome in ARDS. Leukotoxin is produced by neutrophils and macrophages converting linoleic acid into this toxin, which produces the bad outcome in ARDS. There's a fascinating study looking at people on TPN, which is total parenteral nutrition, which is basically if you can't eat and they have to feed you, what do they feed you? Well, what they feed you is glucose and soybean oil. So if they feed you glucose and soybean oil, apparently they increase your risk of getting ARDS by 7-fold. And the study, which I don't think I include here, but you know, the study that does this was basically really good medicine, but really bad science, because as they were doing the study and they realized how harmful soybean oil was to their patients, they reduced the feeding the patients with soybean oil and saw a significant reduction in mortality by reducing feeding of soybean oil. And the mechanisms as described so far would lead one to believe that what's happening is if you put leukocytes in a vial with linoleic acid, they will basically turn all of the linoleic acid they can get their hands on into this leukotoxin, which causes, you know, there's been a lot of interesting commentary on, mystifying to me, on scientists who apparently don't read the literature, talking about how COVID-19 causes cardiac damage and clotting all through the body. And they're like, oh my goodness, why does it happen? Well, gee, guys, this was demonstrated years ago. It's ARDS. Leukocytes convert linoleic acid into leukotoxin. You inject leukotoxin into dogs, which is the study that was done, and they get heart failure and clotting all over their system. So odds are that's what we're looking at in COVID-19 as well. I mean, that seems to be the simple explanation to me.
Let's just be very clear about what we're saying here. And I haven't talked about COVID-19 in months because it's become kind of a boring topic.
I agree.
Yeah, a political boring topic. I think it's very clear that it's connected with metabolic health. But what we're saying here is COVID-19 outcomes are directly linked with overall metabolic health. And that is apparent. What we are arguing for here is that is directly linked with linoleic acid consumption. So let's just be very clear.
They're clear mechanisms.
Yes.
Now, I'm not going to say because it would be crazy that if you cut your seed oil intake tomorrow, you're going to change your risk of getting infected. That's not a fair thing to say, but I would definitely, I think what's fair to say is that this is given the other effects that we're seeing with linoleic acid on metabolic health, it's pretty fair to say that this could be something that predisposes you to a worse outcome.
Exactly. Nobody's talking about infection rates. We're talking about the clinical course and the severity of the clinical course.
That's exactly right. Another fun one, ONA, and I'm not going to go through all the chemical names for these things. But ONA is another common linoleic acid metabolite. It induces arterial calcification in mice, and it appears to do so in humans. This is from a paper back in 2017 that hasn't been reproduced yet. It also induces thromboxane production in plasma and is probably followed by the development of diseases such as thrombus formation and platelet aggregation. So this could be, an interesting, why are people with cardiovascular disease so prone to clot formation? Well, this is a mechanism that could explain it. I don't know. It's not an awesome amount of research in that area that I'm aware of, but it's a pretty interesting finding because it correlates well with the other things that we're seeing. Then we get 2-AG, which is, I guess, a recent favorite of yours, Paul, you mentioned. So let's look at this one. 2-AG is 2-arachidonyl glycerol, which is a metabolite of arachidonic acid, which is a metabolite of linoleic acid. These scientists did this really cool study where they took these poor little mice and they gave them either 1% of energy as linoleic acid, 8% of energy as linoleic acid, or 8% of energy as linoleic acid plus 1% of energy as EPA plus DHA. And what they found was a clear response where linoleic acid induces obesity in these mice, right? Now, we go back to these mice models versus human experience, and that's always a really useful caveat. In this case, however, what's really fascinating is that this study, Alvheim 2012, which I'm sure will make it into the show notes because it's super crucial, was a demonstration of the mechanism of an already approved human anti-obesity drug called rimonabant. Now, rimonabant was approved and then yanked from the market because it had the unfortunate side effect of causing people to want to commit suicide. But let's just discuss the summary of a paper from 2007 looking at this drug. Large randomized trials with rimonabant have demonstrated efficacy in treatment of overweight and obese individuals with weight loss significantly greater than a reduced calorie diet alone. In addition, multiple other cardiometabolic parameters were improved in treatment groups, including increased levels of high-density lipoprotein, reduced triglycerides, reduced waist circumference, improved insulin sensitivity, decreased insulin levels, and in diabetic patients, improvement in HbA1c. So this is a miracle drug, other than the suicide side effect, which is unfortunate. It's a miracle drug. It does everything that we want to do, and it does it by, as these scientists and others have confirmed, blocking the metabolism between dietary linoleic acid into 2-AG. This is, for me, given the fact that it's been replicated at least 6 times that I'm aware of by different groups, this is like, it's a shoo-in. This is like the most obvious mechanism you're ever going to see. Now, I will mention with this paper is why I have a big question with Peter's hypothesis, because this appears to this shows that dietary linoleic acid is inducing insulin resistance, which is the reverse of what Peter's model shows. So there seems to be more that's going on here than Peter's model. There may be some counteractive processes. I don't know, and this is not a criticism, but it's just a statement of ignorance. I don't know how the endocannabinoid system would counteract Peter's mechanism, but that appears to be what's happening. So it's, this is kind of the fun thing about all this stuff is we each come up with two good ideas. There seems to be a contradiction. I don't think either one of us is wrong, but it's something that, hopefully as time goes on, we'll understand why we've got these different effects. Because as I said at the beginning, I posit all of his stuff is true, but this seems to be a contrary mechanism.
Well, when I have him on the show in the future, maybe I'll bring it up and we can talk about it. I think there is, at the physiological level, there is a lot of evidence in humans that feeding linoleic acid actually improves insulin sensitivity in the short term. So that's
Yes.
quite fascinating. And Peter has discussed that, saying, yeah, if you change the F to N ratio, you will remain insulin sensitive. But insulin sensitivity is not always a good thing if you don't want to be insulin sensitive, as your body packs adipocytes with substrate and allows for excessive unabated substrate ingress, specifically glucose and triglycerides. Then your adipocytes get really big and hypertrophic, and that may lead to insulin resistance as well. So there probably are a couple of mechanisms.
And I've got other mouse studies that Peter and I have discussed looking at a high linoleic acid diet in mice where they are leaner than the ones on a lower one. They nevertheless get liver failure, so that's not a good thing. There's a lot of things we don't understand about this. Especially most interesting to me is what they show in this study is that if you give the rats 8% linoleic acid, which causes obesity, and then you give them DHA, they're protected.
Right.
So there's an interplay between different fatty acid types in mice and in rodents and probably in humans that is not really well understood. You mentioned pentadecanoic acid earlier. Pentadecanoic acid seems to counteract some of the effects of a high linoleic acid diet, but again, it's not, weird science trivia points. If you're a dolphin who never eats carbohydrates in your entire life, and you have not enough pentadecanoic and heptadecanoic acids in your diet, you get diabetes. Well, why on earth would a dolphin ever get diabetes? It just doesn't make any sense. But if you add it back in, you cure them. So again, talking about mitochondria and what's happening across different species, there's a lot of stuff going on here that we really don't understand all that well. And one of the interesting things about looking at this stuff is finding these things and trying to wrap your brain about it and explain away some of the seeming paradoxes and contradictions. Okay, MDA, malondialdehyde, I haven't looked at a lot, I'll be honest, mainly because it can be produced by either N3 or N6 fatty acids, and mostly what I've been looking at is the effect of N6 fats on health. However, if you're looking at markers for oxidative stress, MDA via T-bars is the primary marker that's used to detect oxidative stress. In vivo in humans, MDA seems to be mostly made from linoleic acid, but it's kind of hard to show. And it's the most common, as mentioned before, the antibodies against OxLDL, which are looking at OxLDL, are all MDA antibodies. Another funny little science thing, they had an HNE antibody for OxLDL, but then they lost it in the purification process and nobody's ever been able to find it again. I think that would probably be a better marker, but that's what we have. Typically, when you see high levels of MDA, like in OxLDL, you also see high levels of HNE. So that's what I focused on. So HNE. It's the most studied linoleic acid metabolite since it was rediscovered by Esterbauer in the 1990s. It's the major toxic component of OxLDL. It's derived exclusively from omega-6 fats, linoleic acid, and arachidonic acid. So that's kind of what I look at to try and figure out what effects those are having on the body. It's a mitochondrial regulator along with reactive oxidative species. When you and Peter were talking about this, this is a study I got from Peter. HNE also causes the downregulation of ATP production in the mitochondria. And, you know, for similar reasons, it seems to be a signal that there's excess oxidative stress going on in the mitochondria along with reactive oxidative species. So this is a really old pathway, right? This is not, you know, I think it's important to say on a lot of these things, these are fundamental processes. And, you know, my hypothesis is just that we've kind of tipped them over into a pathological level, and this is a good demonstration of that. Glutathione, as we discussed, is an important antioxidant of HNE. Aldehyde dehydrogenase is another important detoxicant of HNE. One of the interesting trivia points of HNE is that it breaks both of those antioxidants. So it actually breaks the regulatory mechanism if it's in high quantities. And it is produced in the mitochondria, as was demonstrated back in 2011 from oxidized cardiolipin. So we have a pretty clear pathway here about how this goes from your mouth to your disease state. HNE is super highly reactive. It damages 27% of the proteins in the cell, primarily around mitochondrial function. You and Peter talked about pyruvate dehydrogenase. HNE breaks pyruvate dehydrogenase, as has been demonstrated in Alzheimer's disease. So what that means for cancer potentially is, you know, the Marburg effect is a shift from mitochondrial respiration to glycolysis, right? Glycolysis in a healthy cell is producing pyruvate to be shuttled into the mitochondria to be oxidized via oxygen. HNE breaks that shuttle and leaves the pyruvate to be oxidized, you know, to be fermented out in the cell. So that's potential. Yes. Now, I didn't. Oh goodness, what's his name up in Boston? I can't remember his name right now, but
Tom Seyfried.
Tom Seyfried, thank you so much. Looked at oxidized cardiolipin in brain cancer and found that the brain cancer model he looked at always included oxidized cardiolipin, and there's a huge literature looking at the effect of HNE on cancer cells. Cancer cells are very averse to HNE. This is a potential mechanism for why that's happening. They also break aldehyde or ATP synthase, aka complex 5. So the point of the electron transport chain is to take substrates like glucose or fats and turn them into ATP. HNE breaks the last step of that chain, right? So it breaks complex 5, ATP synthase, impairing the production of ATP out of the mitochondria. That's a fairly important finding, and it seems to be pretty crucial in Alzheimer's. So in cancer, we have a gene called the TP3 cancer protection gene, right? It's the most common mutation seen in cancers. 50% of cancers have a mutation in this gene. HNE induces this mutation, and that's been shown in multiple different types of cancer. That's a pretty critical finding.
That's scary, yeah.
Super scary, super scary. One comment on a study that I'm sure we'll include, the major lipid peroxidation product HNE preferentially forms DNA adducts at codon 249 of the human p53 gene, a unique mutational hotspot in hepatocellular liver carcinoma, and it's been shown in other types of cancer as well. lipid damage, H&E will turn around and oxidize other lipids, which is how you can get a death spiral in a cell, right? Cardiolipin turns into H&E. H&E goes to the adjacent cardiolipin and oxidizes the linoleic acid. This seems to be what happens in ARDS, where you see this catastrophic conversion of linoleic acid to H&E in the plasma. I mean, it's described, when I first heard about this, I said, oh my God, it's a death spiral. It's described in this paper as a self-propagating chain reaction, which sort of gets to the same point. If you put cytochrome C containing linoleic acid cardiolipin containing linoleic acid and cytochrome C into a vial, it will oxidize all of the cardiolipin until there's none left, without any intervention from any other part of the mitochondria or anything else. H&E induces beta amyloid. So now beta amyloid is really fascinating because we don't only see it in Alzheimer's, where this model was looking at, but we also see it in type 2 diabetes in the pancreas and the beta cells. And to Kenobi's specialty, we also see it in the retina in age-related macular degeneration. And what we seem to have is the exact same process going on in all three places. We have seed oils breaking down into H&E inducing beta amyloid production and poisoning the cell structure that it's in. As I mentioned, it breaks pyruvate dehydrogenase. Another fascinating linoleic acid metabolite, HODGDG, which is A-oxo-2-deoxyguanosine, a pivotal marker for measuring the effect of endogenous oxidative damage to DNA as a factor of initiation and promotion of carcinogenesis, right? So this is the most common DNA mutation seen in humans and in cancer. And the primary cause of it appears to be linoleic acid hydroperoxides, which produces much higher levels of this than other RAWs like H2O2. The last one, because I'm running out of energy here, and I think we may be running out of time, 13-HOD, which you mentioned with Peter. We won't even get into the cancer aspects of this. Let's just talk about asthma, which is a pretty common disease. 13S-HOD causes severe airway dysfunction, airway neutrophilia, which is basically the macrophages, the leukocytes attacking the airway. Same thing we see in ARDS, mitochondrial dysfunction and epithelial injury in a naive mouse model. So, you know, give a mouse 13-HOD and you can induce massive asthma reaction. Very similar to what we see in ARDS. So, questions?
And I'll say with regard to asthma that we know that asthma is very responsive to oxidative stress, and we can give asthmatics glutathione and see them do much better. So it's not surprising that there would be oxidative products of linoleic acid metabolism in that condition as well. 8-hydroxy-2-deoxyguanosine, one of the last ones you mentioned, is measurable. There are profiles. You can check this. I've checked it on myself. It is an indicator of DNA damage, but you guys can also check that. You can check your lipid peroxides. But I think that what we're getting at here, and I appreciate, Tucker, you going into all that detail about the different products of breakdown of linoleic acid, which is fairly technical, so people can re-listen to that. But let's just bring it back for people at a high level. If all of this...
The point of going through all this, and yeah, it's too much, and I can't tell you how much stuff I left out. But when you start discussing about this stuff, it sounds crazy, right? Because there are so many areas, if you go through the literature and you look at chronic and age-related diseases and the interaction of these metabolites, they're involved in everything, right? It sounds crazy because you're saying, oh, this one thing causes this and that and this and that and the other thing, but there's a literature to support it, right? It's not just oh, I mean, I don't know. There's so many, frankly, quack nostrums out there. The difference between this and everything else that I've looked at, and I've looked at other potential causes, is that this has a very high explanatory value in that populations of humans only seem to come down with these diseases when they have industrial diets introduced, right? Which include linoleic acid going back 150 years ago, right? And when you start looking at the demonstrated mechanics in the literature, there are clear reasons why this is happening, right? I mean, not always perfectly clear, but there are, plausible pathways that explain why, if you look at the epidemiology, you see what's associated. Well, obesity is associated with diabetes, with heart disease, with cancer, right? All of these things with, depression, right? All of these things are linked to each other. And when you start looking through at it from this mechanistic perspective, you start seeing the exact same processes going on. You see cardiolipin oxidation leading to mitochondrial dysfunction, leading to inability of cells to oxidize substrates, leading to production of these toxins like HNE, which creates a signal that causes macrophages to attack these cells, which leads to inflammation from the macrophages producing cytokines, which causes more macrophages to come in, which causes cellular dysfunction, like you've talked about with adipocytes not being able to divide the way they should. And what you pretty quickly realize is that the mechanisms in all of these different disease states are common. There's one process that's going on, and it's a cellular process, right? It's not an organ-specific process. It's the fact that all of these cells contain mitochondria, and the mitochondria are breaking down in a common way, and it may have different effects on different tissues, but it explains why we're seeing all of these related and correlated diseases happening in all of these populations all over the world. And I don't think there's anything, well, let me rephrase that. I haven't seen anything else out there that has the same explanatory value. And I'm, perfectly willing to, I got to this point because I came up with some hypotheses and debunked them, right? This is what I was left with. It's entirely possible that I will wind up debunking this one as well, but I've been trying for years, and all I do is keep coming up with more evidence as to why it's correct.
And I agree with you. I'm right there with you, shoulder to shoulder, in agreements that this is the most compelling hypothesis that I have seen to explain the explosion in chronic disease, obesity, diabetes, cardiovascular disease that free-living humans appear to have experienced over the last 150 years, because ultimately that's what we are tasked with explaining. No person out there can deny that humans have become massively basically fragile and unhealthy over the last 150 years. And I may have said 150,000. I just meant 150. But, the last 150 years, we've become Homo fragilis, and something has happened. And so at a very high level, we are looking for evolutionary inconsistencies, what things have changed in our diet. And some people would claim it's just because we're eating more, which I think is a load of bullshit. It's not because we're eating more. The calories in, calories out bros are full of it.
But that's not fair. We are eating more, right? It's easily demonstrable that carbohydrate intake has gone up. But then you can turn back around and say, well, but gee, 2AG induces that sort of behavior.
It's true.
With increased linoleic acid intake, and then that's exactly what we're seeing in the human population. So that's not even a contradiction. That's a confirmation of the hypothesis.
I guess what I'm saying is just that I don't see any mechanistic data or any data to suggest that slight overconsumption of calories is going to lead to this cascade of metabolic dysfunction and cellular problems. You can give people a little bit extra calories and they will gain weight, but I don't see a real mechanism that leads to this degree of mitochondrial dysfunction and on down the line. And so what we're dealing with here, if the listener is feeling overwhelmed with all of the topics, what we're essentially dealing with is pointing out that the major evolutionary inconsistency is this excess consumption of linoleic acid in seed oils, in animals fed corn and soy, in excess consumption of grains and seeds and nuts, things that our ancestors would never have access to. So you guys, that's what we're talking about here. And so Tucker is presenting a ton of really detailed evidence. We definitely got in the weeds, but the take home is just eat like your ancestors. And they didn't eat this much linoleic acid. Vehemently avoid oils, seed oils, really focus on animal foods, eat nose to tail, eat like your ancestors, not like your doctor. Get organs in your diet, either fresh or desiccated. You like that? And you will thrive. And we've seen that. I mean, Tucker showed multiple studies, and there will be many more in the show notes with non-alcoholic fatty liver disease. The removal of linoleic acid results in total improvement. That's earth shattering. That's tectonic, and Western medicine turns a blind eye to it. There are so many chronic diseases that we go round and round in Western medicine trying to solve. And I really believe the evolutionary consistency, the major misstep in human dietary change and patterns is right in front of our faces. And that's what we've been talking about today. I just want to show one more study because you mentioned it here at the end, which is the fact that 4-HNE does appear to impair adipocyte biology. And this is something I talk about with Ben Bickman. And they show that with physiologic low concentrations of HNE, sufficient to promote oxidative stress, impaired adipogenesis. That was something I got really interested in. Alter the expression of adipokines, which are the hormones signaling the fat cells to actually divide. Impaired adipogenesis leads to adipocyte hypertrophy and increased lipolytic gene expression and increased free fatty acid release. This, I believe, is some of the main central pathology around metabolic dysfunction. We also saw that at the level of the macrophage, at an immunologic level, there are cytokines that can be elaborated when OxLDL is binding that could also contribute to that process. But that's fascinating for me when I was able to make that connection.
And those are happening in parallel. I mean, you're seeing
exactly
fats. Stefan Guillenet did a great paper looking at fatty acid composition in adipocytes over the 20th century, showing that there was a huge increase in linoleic acid, which correlates to the huge increase in the diet shown by Christopher Ramsden over, 1,000-fold increase in linoleic acid from soybean oil over the 20th century. And the key thing to note, the key thing to be aware of is that linoleic acid is so unstable that it auto-oxidizes even if it's just sitting in your cells, right? You don't have to have it sitting in a jar for it to oxidize. If you eat enough of it, it will build up in your cells and it will oxidize there, right? It's going to turn into HNE. This is shown in the literature in adipocytes. It's going to prevent your adipocytes from dividing as they should when they're healthy. It's going to turn into this, I didn't even really get into this, but basically oxidized linoleic acid is indistinguishable to your body from a bacterial infection, right? You are creating an autoimmune condition in your body, and that's what's causing macrophages to come in. And that's what we see in obese adipocytes, is that they are being attacked by macrophages, and they have this inflammatory pathology going on, which the simplest explanation for is, it's oxidized linoleic acid. That's what, I mean, you're a physician, you can tell us what this means. If you have a staph infection, that's about as bad as it gets in your body. And yet, by eating seed oils, you are mimicking a staph infection in your body to your immune system. I mean, this will get us kind of off topic a little bit, but it's the exact same mechanism that happens when poison ivy, which also is caused by polyunsaturated fatty acids. Nobody eats poison ivy. You'd have to be out of your mind. And yet we all eat seed oils, which have the exact same metabolic effect on our immune system as eating poison ivy.
It's striking. It's striking, Tucker. And I so appreciate your work. Yeah, I love it. So hopefully that ties a bow in it and people can see it. But I always like to pull it back to the evolutionary lens and just think, what is the evolutionary inconsistency? Why are we doing this? It's completely evolutionarily inconsistent to eat this much seed oil. And I think that everyone listening to this, and your mom and your grandma and your brothers and your sisters, will benefit massively by making these changes. And of course, you guys all know, by including animal foods and organs in your diet as well. So thank you so much for your work, my friend. Is there anything you wanted to say before we wrap up?
Amen to all that, Paul. Keep up the great work. You're really doing a great message here. I think you're spot on.
I so appreciate your work too. So the last question I always ask my guests, and thank you for sticking with me for this podcast. I know we went a little long today, is what is the most radical thing that you have done recently, Tucker?
Oh, Lord. I don't know. I'm pretty boring, I hate to say.
So do you have any backcountry skiing plan for this winter? I don't think you're boring.
Well, yeah, I guess boring's a matter of perspective. I mean, I've got a lot of backcountry stuff planned this winter. We finished up, my girlfriend and I finished up our ski season last year by backcountry skiing up Mount Marcy in the Adirondacks, the highest mountain in the Northeast, which was pretty phenomenal. Probably, I guess, the most radical thing I did, so my girlfriend and I went to high school together and got back together last year. And when we met up, she, you know, how do I put this delicately? You know, same thing that happens to everybody as they get older, it happened to her. And it turned out she was a Grieger vegan, God help me. And I was like, oh no, this is just, what a mess. And so she asked me how I ate, because I looked so thin compared to everybody else our age. And I told her in a sentence, I said, avoid seed oils, avoid wheat, avoid refined carbohydrates, and eat lots of meat and animal fats, right? And it was sort of I don't want to talk to you, but I'm going to respect you and give you an answer comment. And I, Grieger vegan, she's never going to listen to me. 2 weeks later, she gets in touch with me and she says, well, I've lost 17 pounds so far. And I was like, what? And in 2 months, she lost 56 pounds. And unbeknownst to me, she put her fibromyalgia, which she'd been suffering with since her 20s, in total remission. She had been in pain for almost 30 years and it's gone now. And so she's my partner in crime in running and backcountry skiing now. Is, occasionally I post stuff on Facebook about that. So that was probably the most radical thing that I've done. I was so blown away by how she took that throwaway sentence and transformed her life with it. And I think that's just a great example of how what Paul and I are talking about, it's not hard, it's not complicated. Just a little bit of information like that, and you can just totally change your life.
That's amazing. I love it. Thank you for sharing the story. That's incredible. And it's the same kind of stuff we hear at Heart and Soil when people include organs in their diet. It's just all the same ideas. Just eat like your ancestors, understand how your ancestors ate. We went really deep in the science, kind of supporting the notion that linoleic acid and its metabolites are dangerous, but that's all kind of fun for us. And so we can actually sleep at night and say, the science supports what we're doing, but the high level is there for you guys too. So Tucker, where can people find more of you in the future? Because I'm sure they're going to want to consume more of your content and support you.
Well, I'm very active on Twitter at Tucker Goodrich, and my blog is Yelling Stop, which is a nod to Paul's comment about returning to an evolutionary concept in our health. Yelling stop is that we're heading in the wrong direction. We need to go back to the thing that worked. And I'm sure we'll have a link to that in the show notes. But yeah, Twitter's probably where I'm the most active.
Awesome. Well, thank you for coming on, my friend. It's been a pleasure.
Thank you for having me, Paul. It's really been a pleasure.